Hello everyone, it is February 18th, 2025, and this is the libhal biweekly meeting. All right, so for our agenda today, we're going to go over some additional instructions that will be added for Ubuntu 24.04, but mostly actually this is really just about moving everything over to pipx for any commands like conan or pyocd and that kind of thing. We're going to go over some fixes that happened with bitbang I2C recently. We're going to go over a couple of new errors, device or resource busy, and also function not supported. And then we also have a new HAL serial interface. It's actually an old one, but I haven't talked about it, I don't believe, in all of the slides. So I made some slides to discuss it. And then finally, I'm going to go over the libhal 5, the 5.0 changes, how they've been backported to 4x. And I don't really have a section to talk about this, but I think I can kind of do it now. I'm able to backport quite a few things into 4x and migrate it over. The only thing that I'm not certain I can do is do the same thing for interfaces that are already existing. And I guess I'll show you that in a sec, or show you that in a little bit. So let's get started. All right, so basically the additional instructions for Ubuntu 24.04 is that we're going to migrate everything over to pipx. And actually, we're just going to do that unilaterally for everything. This came in because of Ubuntu 24.04, just giving error messages about, hey, you should be using pipx and that kind of thing. I've seen other people's computer do the same thing. I will make sure that everything's moved over to pipx because that's the correct program to manage applications that are run and held through pip, whereas normal pip is just for bringing in libraries and such. If just using normal pip works for you, you can continue to use it. I would recommend moving over to pipx, but you do you. All right, fixes to HAL bitbang I2C. So here's what was observed. We were doing some experiments where one application would work with the MPU 6050 and another one would terminate. Now, what we were trying to do is the two projects weren't using the same exact code, but they were very similar. So they're trying to figure out why exactly does this very similar code seem to operate so differently. One would terminate and the other one would just operate as expected. The only difference that we ended up finding out was that one of them was doing a HAL probe on the I2C port prior to getting into constructing the MPU driver and then going from there. So the root cause had to do, we ended up finding out why this was happening. It's because something about the probe not being there would result in the first transaction on the I2C bus being a NAC. And if you try to construct an MPU 6050 driver, and the first thing it'll try to do is talk to the driver to ask it, hey, what device are you, to get an ID. And then it confirms that the ID is correct. If the device NACs, it thinks, okay, the device is not on the bus, I'm just gonna throw an exception at this point. Or let the exception propagate out. The real source of this root cause came from the output pins being passed to bitbang I2C that can basically be at any state. And because they can be in any state, there's a chance that when you do configure and you change pull up, pull down state and all that, or if before it was passed into the bitbang I2C, it was like someone had toggled the signals a bit. If you've done something like that, our way to get out of this is basically to run probe twice, and that should hopefully get the bus back into a decent state. And if we find out that doesn't exactly work, we can look back at how we initialize bitbang I2C to ensure that the first time you use it, it always acknowledges, or it acknowledges as long as the device is there. All right, so we have a new error type. It's raised whenever attempting to acquire a resource if there are none left. So for example, if you have a CAN bus manager and you want to acquire a CAN bus manager, you have a peripheral manager for managing the CAN bus peripheral. We want to get a bus manager so you can change the baud rate and you can set up other things. Only one bus manager is allowed to be alive at a time. And for things like so if you try to acquire it twice, basically the second time you try to acquire it before you destroy the previous object, it'll throw an exception. So you would need to basically this is a way to device and resource busy is a way to indicate that, hey, you're trying to acquire a resource that does not exist anymore or is currently being used somewhere else. Yeah, that's pretty much that. In cases where you have multiple of a resource, like for example, filters, where you might have like 15 filters or 7 filters or a certain number of filters, you can keep acquiring them until you run out of completely all the resources, in which case the acquirer should throw device or resource busy. And the only real solution to this is that either A, you have a bug in your code, or B, you have some alternative that you can execute in place of acquiring that resource. You can have backups, but I think in general, in most applications, if you get this thrown from a program, it really just tells you what type of bug you have versus being something that's actually recoverable. This is also kind of similar. There's another error called function not supported. It is raised whenever attempting to call an amended virtual function API that has not been overridden. So I've been thinking about the interfaces that have changes that I could make, but would either be breaking API changes, or I tried to come up with ways to shim some of the old stuff into the new stuff, and that was not working out actually. I found technical reasons why I can't have the callback functions that take no arguments, then take a tag. So, and also the onWait function doesn't exist currently on IOWaiter, which is where this is going to go to. I was thinking to myself, all right, well, I want to be able to build out the code with this API existing. How can I go about doing this? And the answer really comes down to just add an exception. The default implementation of this API is to throw a function not supported if it's not supported. And the idea is that you can do the same thing like with device or resource busy. You can have an alternative in that case, but in a lot of cases, I think that won't really exist. I think the majority of cases will be you realize at that point that you've chosen the wrong implementation, or that you need to talk to us or whoever implemented this for you to implement this API. But hopefully, once we move to 5.0, the old APIs will basically be any old APIs that did not have tagged callbacks. Those will be deleted, and then the functions like these that have this safe throw here can be turned into pure virtual functions. They become mandated. So this might be our way of going about adding in amended APIs, and then later on deprecating and then removing things. So yeah. So next up, we have the new HAL serial interface. Now, it's currently been in the code base for a while. It's actually called zero copy serial. It is in the directory zero copy serial. I should have put it inside of serial, and I might, in a way, move the implementation to serial so you have them in both. My goal is actually to take zero copy serial and make it the new serial. I think it's the right choice for the serial API. I made this other class just so we would have it so we could work on it. This is one of those cases where if I make all the changes, I still need to actually change things from zero copy over to normal serial. But the way it works is very similar, nearly identical to how CAN transceiver works. You have a configure function, and because there's only one serial is 1-to-1, there's a single serial configure, and it's not put into its own interface like we do with CAN manager and all of that. And it sets the baud rate and everything else you'd expect with serial. It's all the same exact settings from serial, so nothing's changed there. The write API is identical. You just give it a set of bytes and it sends it out. The receive buffer and receive cursor are the new things. So just like with CAN transceiver, we actually expose the entire circular buffer for serial. And we also expose the receive cursor as well, so you know where their last write has happened. And that can come straight off from a DMA register for count for how many things you've written into the buffer. The idea here is that I was noticing that there's a lot of cases where I actually don't care about getting a copy of the data. I really just want to evaluate the data from the buffer. And because serial is kind of 1-to-1, not kind of, it is 1-to-1. I think code could call receive buffer, get the length, and go, okay, cool. The length of this thing is 3 times as much as I need for what work I'm going to be doing. Well, I don't know if that's going to be simple. Maybe we can do some code that kind of checks to see the receive buffer is big enough, and then if it is, then it can just like not have to do um, any actual copies. It could just simply read the values out of the buffer directly, and then pull out the like text and stuff like that. It can parse the information out of the buffer directly, out of the serial buffer directly, versus having to copy it into another buffer and then perform the parsing from there. I think this is the more optimal way to do serial in a lot of contexts. So that's why we've gone with this. And then finally, we have backports. So here are the things that I've already backported over to libhal. It's in 4.10.0. We have ADC 16 and 24. It'll return back a value from 0 to 2 to the power 16 minus 1 for ADC 16, and likewise for ADC 24, but for 24 bits. There's no precondition or postcondition for this function. There's no way that this value could ever be a value outside of this range. Although technically this function, once we can move over to C++26, would have a postcondition of the value being returned not exceeding 24 bits. Fun fact, C actually added in a thing called a bit int, where you can specify the number of bits you want to deal with. So you can say like 9 bits or 12 bits, and I think it's supposed to have the same semantics as a typical 16-bit or 32-bit number, such that if you were to add two numbers that are 9-bit to each other and it overflows, then it still stays within 9 bits. And to be fair, I actually think that makes a lot of sense. Like, you can just simply look at less bits. You can just simply, whenever you pull out the data, either, extract it through an AND operation, or after the operation is finished, you can then perform an AND operation to clear out the extra bits. So it might be a little bit more costly, but at least you know that your number will always be within that range. So that seems really cool. I think C++ is actually considering adding in that feature. So considering it, not saying that they will. I saw some emails about it. Backport DAC 16. So same thing. You can write a value from 0 to 2 to the power 16 minus 1. This will be proportional to your value that you have on your DAC. Oh, I want to make one thing clear. Let me go back here. You may be wondering, okay, well, ADC 16 is cool, but what if my ADC is 12 bits or 10 bits or 8-bit? How does this work? I might have talked about this before. I'm going to reiterate it again. We use this particular technique called upscaling or bit upscaling. What it does is you basically take, let's say you have an 8-bit value. You can take the 8 bits, shift them up to the uppermost byte of a 16-bit number, and then duplicate the bits down most significant bits first. Or basically just duplicate the bits onto the last byte. By doing this, if your ADC responded back with a 0, the answer you'd get by doing this duplication would be 0. If you got back 255, which would be all ones, and you duplicated the bits, you get basically 2 to the power 16 minus 1. So you get the full range from 0 to 16. You don't have to do any other extra math as well. You kind of just have a number that you can guarantee is always going to be between 0 and 2, the maximum 16 can be, or a 16-bit unsigned number can be. And the proportions are about the same. So the cool thing about doing the duplication is that it preserves a lot of the proportionality of the numbers. So they're a little closer than if you had just used all zeros or all ones in the missing space. So yeah, that's pretty much how that works. Same thing with DAC. The idea is that in reverse, you give it a number. Let's say you give it like 32K. So that's half of 64K or half of U16 maximum. Let's say your DAC is only 10 bits. Well, you'll just put the most significant bits of the percentage value you have into your DAC, and it gives you basically the best approximation to the number that we wanted. If an application wants to ensure that their DAC is 16 bits, I think they should just simply look for a driver that fits that, just like how you do the same thing when it comes to hardware. Yeah, so that the interface is not built to guarantee you 16 bits. It is there to be a clear way to transmit that information to the necessary bits or registers in the hardware. Next up, we have the backport for PWM. That is PWM 16 channel and group manager. Now, you might have noticed this with the previous DAC driver, but there's no like 24-bit DAC. There's also no 24-bit PWM. And for the most part, I'll add those if people really need them. But until people need them, we're going to stick with just this. I think 2 to the power of 16 is a lot of precision. You get a lot of precision out of that. So I thought it makes sense just to kind of stick with that as our duty cycle and our DAC writing value. And if people need more precision, we can give them that precision. So with PWM channel, what really separates it from the original PWM is that the original PWM had a frequency function that accepted a value, and you could change the frequency of the PWM based on that value. This, I had spent a lot of time thinking about if that was an okay design decision for PWM, and I think I finally cracked and was like, no, that's a bad idea. I think it's bad. We should not do it. We should stop doing that. Here's the issue with doing that. If you have like 16 PWM channels and they're all sourced by the same clock, meaning that if you change the frequency of one, you change the frequency of all the other ones, there's no way for any of the code to be able to just manage that. I think it's kind of unreasonable to have code to be able to deal with that kind of situation. And there's no way in the code that kind of makes it clear that that's what's kind of happening. It makes it seem as if somehow each one of the PWMs can independently control their own frequency, which isn't really true. What really happens is that you have a set of channels inside of a group. So this doesn't exactly fix this problem, but it does separate it out a bit. So one, we have this PWM channel 16 channel, which gives you a frequency function, so you can check to see what the frequency of the PWM is, see if it's within a range that's acceptable for your application. And then we also have a duty cycle that takes a U16 proportional value. You can no longer control the frequency. You can just return back and get the current one. If you want to control the frequency, you need to use a PWM group manager. This manages the group of PWM channels, and from here you can change the frequency. Now the idea is that most drivers would only accept PWM 16 channel as their input. They get one of those. Every person just gets a single one of these. These aren't shareable. I mean, you could share them, but like they're not meant to be shareable. But the group manager kind of controls all of the different channels underneath it. And in general, I would think that the PWM group manager wouldn't be given to any driver unless it's like important that that driver have that. And if you needed to do both like PWM control and duty cycle control, you'd have to accept both the PWM group manager and the PWM channel. And I don't know if there's any clean way to symbolize this in the code, but basically if you did that, you'd want to not use any other channels from that PWM unless you also can accept the changes in frequency. Yeah, this might be us trying to create a set of abstractions to represent PWM in a way that might be a little too complicated, but I do think that it's important to remove the ability to change the frequency from all drivers that use PWM. I think it's too powerful of an API to just kind of let be there, because then anyone can just kind of make that change and screw up a lot of the code. At least with this, you can see when someone's passing it to something and go, oh, wait, hold on, that's a code smell. Why are you passing it in? Why does this thing have that kind of control? And then finally, and probably the one that I'll enjoy explaining the backport for the most would be SPI channel. So there have been some pretty large changes. It's very similar to SPI, but, well, actually, I would say it's the only thing that's really similar about it is that it's SPI. That's pretty much it. The transfer function is identical. There's supposed to be a byte equal filler, but I removed that stuff just to make it more concise. SPI channel represents not only an SPI, but also a chip select. In the past, I separated these, but I separated these away from each other because I didn't like the idea of how I kind of saw SPI generally, where it's you have a specific chip select for that SPI, and whenever you perform a transaction, that chip select is selected for that entire transaction. I didn't like the automaticness of that because what it meant you had to do is if you wanted to send over a kilobyte of data and then read back another kilobyte of data, in order to do that, you need to allocate 2 buffers. One for the first kilobyte and the one for another kilobyte of data. Or maybe have some sort of flow control type API in order to control the chip select, which is actually what we do here. But basically, in a lot of APIs that I've seen in the past, they don't give you like direct chip select control. They just say, "Hey, give me your transmit buffer, your receive buffer, and your links for these, and I'll send it out for you." That makes it it's not very ergonomic. It requires a lot of RAM. You have to have everything contiguous. You need to load up and pack everything correctly. Not correctly. Pack everything in the order it needs to come out in. Another option that I think is better is to simply allow the user to control the chip select as they see fit for the application that they're doing. So here's how SPI channel works. So first thing I'll actually go into, which is something that's kind of similar from before, but a simplification. We have different modes. So SPI comes with mode 0, 1, 2, and 3. What those modes do, you can look at Stack Overflow, Wikipedia. It's in the docs. But basically it changes the clocking and when the data lines are sampled. I used to explain these more verbosely in like Boolean values. And although the code size between, I bet this, given padding and like, being aligned to 4 bytes, I bet the actual overall size of the settings didn't actually change. But I didn't like how confusing it was to look at a data sheet, see that it says mode 1, and then try to figure out which settings you need to set to make it be mode 1. So I was like, all right, let's just go with mode 1. And if at any point people want a way to specify the clocking more explicitly, we can write an API and a helper for that. Like to mode, and you give it the enums that you want, and then it'll do the thing for you. So that's how you set up your settings. Now, the cool thing about configure is that it actually doesn't configure the bus. It stores your settings for later. And I'll get into how that works in a bit. Actually, I'll get into that now. So the idea here with SPI channel is that we have this chip select. In order to get control over like the bus, you set chip select to true. That'll assert your chip select, or at least first thing it'll do is check to see if the bus is busy, and when it's no longer busy, it'll try to acquire access to it. When it acquires access to it, it'll lock, or it'll basically hold some sort of lock over the bus itself. It will assert the chip select, which is usually pulling the line low. And then from there, you can do as many transfers as you need in order to channel the data that you need. Then you can do chip select false in order to deselect and to release the bus, and then the bus can go from there. Now, the cool thing about chip select is that, and configure now, is that the responsibility of knowing where the settings were are now held inside a SPI channel. Sorry, I think someone's talking. Hold on a sec. Okay. All right, thank you for muting. Where was I? Yeah, so chip select. The idea here is that when you pass the value into configure, it saves the settings. And when you assert chip select and acquire access over the bus, there's also one other step which configures the bus to fit your settings, at least as close as it possibly can. So let's say you said you wanted to operate the clock rate at 1 megahertz. When you do chip select and acquire control over the bus, that'll configure the bus to that clock rate, so you can do all your transfers at that clock rate. This way, you can basically set the clock rate to the maximum you can tolerate for that device, and everyone's always talking at the maximum speed that they possibly can, versus having to remember to reconfigure the bus anytime you need to access it. This kind of puts all that information all into one place. It does put a lot of onus on the SPI implementation to ensure that the channels are properly arbitrated between, but I think it's worth it in order to make SPI channel a interface that can be used in any of the drivers without having to really be concerned about the whatever other things are using the same bus. I think you could just write it, implement it, and go from there without having to worry about the rest. Now, it might be weird why we have clock rate here. Generally, in libhal, we don't actually provide accessors for things that you can set. The reason why is because you set it, you know what you set. We tend to not change those things. But in this case, clock rate, it can be changed. So if you put in 100 kilohertz and I'm sorry, 100 kilohertz. Let's say like 12 kilohertz. I'm sorry, 12 megahertz. Let's be more specific. 12 megahertz, and you need the clock rate to be exactly 12 megahertz because you're actually using SPI as a signal generator, or using SPI for a particular use case where communicating slow is unacceptable. You can ask for the clock rate, and it'll give you back the approximate clock rate that it expects it'll be able to reach based on how the hardware can handle it. So you can actually set any arbitrary value for clock rate, and if it's above what the actual SPI hardware can support, it'll just clamp it down to the maximum that it can support. Yeah, and that's pretty much that. I recommend that all drivers that use SPI channel in the future set the settings to the maximum that the chip you're working with can handle, and then let the SPI channel hardware bring it down to a level that's actually reasonable. And then you can do all your communication at that level. And if you need to have it at a very specific value, you can then check the clock rate in order to get that information. The astute may also notice that there is a lock and unlock function. Lock just calls chip select true, and unlock just calls chip select false. Why are they here? I tend to not add in extra helper functions, but I really want to be able to use this API, the interface, with standard lock guard, so that you can put lock guard. I would rather no one actually call the chip select function. It would be kind of crappy to call that. Same thing, don't call lock or unlock directly. You should use standard lock guard on the SPI channel. That'll acquire a lock for that channel. Then you can use transfer as much as you like, and then when the scope gets cleaned up, the SPI channel would then be unlocked. That's pretty much the idea here, is anytime you try to use SPI channel, you have to acquire a lock. And if you're single threaded and the locks are all atomic, then this can be rather simple and performant. And if there's no other devices, there's only one single SPI channel, you'll always have the lock available because locking it would always never have any blocking to it. Do understand though, when you do chip select true, this will block until the channel is available. So another blocking API to keep in mind. And then we have transfer. And one thing about transfer is that I was trying to figure out what the behavior should be if you have chip select is false and you perform a transfer. And one option is to throw an exception, to simply say, all right, you're in the wrong state, and then to throw an exception. I kind of hated that though. I didn't like the idea that there's a precondition on transfer that chip select be false. And even if that was true, then I would feel compelled to add another vtable function, another virtual function for checking to see what the chip select state currently is. But now what we'd end up doing is adding a lot of extra checks in the code anytime someone wants to call a transfer, especially if they call a transfer in some other deeper function where it may not be exactly clear if chip select has been selected or not. So the alternative that I went with in order to eliminate all of that is to add a little bit more logic to transfer. What transfer does is it will if chip select was false before, transfer will basically acquire a lock temporarily for the duration of its transfer. It'll then perform the transfer, then it'll unlock the access over the bus, and then it will deassert the chip select and then continue on. So you can actually use SPI channel without having to use chip select at all, just by using transfer. And that's totally safe and totally acceptable. Chip select is actually there so that you can do multiple individual transfers with different data from different locations. I considered using a span of span here in order to kind of, in a way, eliminate the chip select need. But there's going to be cases where code needs to, not all the information will be known immediately, and you can just pass the span of span in. You may need to actually do separate steps in between things and then recalculate what you need to send out. So this is the API as it stands for now. I have not moved to span of spans yet. I think I might do that for serial, but for now, we're going to keep this as it is now. Span of span is super important, though, for USB. And that's because it has to bundle. It needs to fill up a bucket of memory, like a section of memory, and then dispatch that out. So a span of spans is super useful there. But yeah, that's pretty much that. And that's pretty much it for this week's meeting.